Hello again. This is Math 1120 coming to you from the College of DuPage, and this is the conclusion of the lecture entitled Conditional Probabilities and the General Multiplication Rule. When last we left off, you were working on this problem. I hope you finished it, but just in case you didn't, I'll give you some more time. You know what to do. Let's see how you did. Well, we used the definition of conditional probability we had last time. So the probability that is raining given that it is cloudy is the probability of rainy and cloudy divided by probability of cloudy. We plug in the numbers and we get this answer. Now this motivates the general multiplication rule. So the probability that two events E and F both occur is the probability of E and F, and if they were independent we just multiply them, but now we're allowing for them to depend on each other, is the probability of E times the probability of E given probability of F given E. Now this is just an algebraic change in the definition. We'll multiply both sides by the probability of F given E. In other words, the probability of E and F is the probability of event E occurring times the probability of event F occurring given the occurrence of event E. This is worth thinking about a little bit. So we're going to use that to in this problem. So the probability of driver who is speeding gets pulled over is 0.8. The probability that the driver gets a ticket given that he is pulled over is 0.9. What's the probability the randomly selected driver who is speeding gets pulled over and gets a ticket? So that is an and. So the probability of E and F, or is speeding, gets pulled over, and gets a ticket, is the product of these two, which is 0.72. Okay, here's another problem for you to do. According to Center for Health Statistics, this is the probability the randomly selected resident of the United States 18 years or older is a smoker, and there's a 44.5% probability that a randomly selected resident of the United States aged 18 or older is female given that he or she smokes. What's the probability that a randomly selected resident of the United States aged 18 or older is female and smokes? And would that be unusual? You know what to do. Let's see how you did. So the probability of female and smoker is the probability of female given they're a smoker times the probability they're a smoker. These are the numbers. We multiply them and we get that. Now, this is not unusual because by our definition it is greater than 0.05, so it's not unusual. Now this problem deals with acceptance sampling. When a shipment comes in, they really don't check to see if they're all good. They just do a sampling technique. That's what this is about. So suppose that of the 100 circuits sent to a manufacturing plant, 5 are defective. The plant manager receives a circuit, randomly selects 2 of them, and tests them. If both of them work, she will accept the shipment. Otherwise, the shipment is rejected. What's the probability that the plant manager discovers at least one defective circuit and rejects them? Okay, now we're going to use 2 approaches. And the first approach is to draw a tree diagram. So the first circuit is either not defective or it is defective with these probabilities. The second circuit really depends on the first circuit because you don't throw it back in, you select a second circuit. So the probability that this first circuit is not defective is, and that's given that the first one was not defective, is 94 over 99. And so you multiply those two and you get 0.902. And then we can look at the second, and we have the branch. Okay, so every time we get a branch, so here it is not defective, here it is defective, here it is not defective, here it is defective, here it is not defective. Here it is, defective. And again, these are conditional probabilities based on what happens. It is useful thinking about this tree diagram, though, because this is something we'll use later. So anyway, if we go up this branch, we get neither one was defective. If we go this one, we will get let's see, we will get the first is not defective, the second is defective, and so on and so forth. So we have all of these things. Now the probability at least one defective is the probability that we go on branch G, D, plus the probability that we go on branch D, G, plus the probability we go on branch DD. Now these things are disjoint sets, so we just add these probabilities and we get this. Now, so this is the probability that the shipment will not be accepted. The other way is to just say the probability at least one defective is 1 minus none defective, and that is going to be 1 minus the first not defective times the second not defective, given the first is not defective. This is a conditional probability because there are differences depending on what you pick the first time. So what you pick the second time, the probabilities depend on what you pick the first time. Well, we do the calculation and we get exactly the same answer. Here's a problem for you to consider. Suppose you just received a shipment of 6 TVs, 2 are defective. You pick 2 at random. What's the probability both of them work? And then what's the probability at least one of them does not work? You know what to do. Let's see how you did. Probability that both works. Here's the equation for that. You do the arithmetic and you get 0.4. The probability at least one television does not work is 1 minus the probability both TVs work. And this is the answer you get. So that is the answer for the first part. This is the answer for the second question. Whenever a small random sample is taken from a large population, it's reasonable to compute the probabilities of the event, assuming appendance, sometimes. Okay, so here we're talking about this, and the problem is, in a study to determine preferences for self are more or less preferred than preferences for others, research first asks the individuals to identify the person who is most valuable and likable to you, or your favorite other. Of the 1,519 individuals surveyed, 42 chose themselves as a favorite other, and this is a study that was done. Suppose we select one of these 1,519 people. What's the probability that he or she chose himself or herself as their favorite other? So if 2 individuals are selected, what's the probability that both chose themselves? And compute the probability of randomly selected 2 individuals who selected themselves as their favorite other, assuming independence. So we go through and we compute this. Here we compute it using the general multiplication rule, and you find that we get this number. If we do it assuming independence, or we multiply, we get a very close number. So you see, this says that if you have a lot of people, a lot of individuals, and you're taking a sample from them, can you assume independence? And here is the rule of thumb. If a small random sample is taken from large populations without replacement, that means you don't throw them back in, it is reasonable to assume independence of the event. As a rule of thumb, if the sample size is less than 5% of the population size, we treat the events as independent. Okay, so here is a problem for you to consider. A chip company has just shipped 10,000. That is a big number, but 50 of them are defective. So compute the probability that 50 of them are defective using conditional probabilities, and then compute it under the assumption of independent events and compare and see if it mattered much. And so here we go. You know what to do. Let's see how you did. Okay, so this is actually using the fact that they are that these are dependent events. It matters what happens selecting two defective chips. So there's 50 chances out of 10,000 to get one here, and if you did that and you went to the second one, there would be 49 out of this many. If you do the arithmetic, you get this. If you just take the probability of selecting two defective chips and you assume they're dependent, because 50 is less than 5% of 10,000, you will get this, or excuse me, 2 is less than 5% of 10,000. Our sample size is 2. You get this. So the difference is not significant, and so we're using that rule of thumb. We can go back now and redefine, or maybe define for the first time, what does it mean for two events, E and F, to be independent. So two events, E and F, are independent if the probability of E given F is equal to the probability of E, or equivalently, if the probability of F given E is just the probability of F. You see, it really doesn't matter whether E happens or not. And if we do that, then we do see our old rule about independence, so this just kind of confirms that. And so this is another definition of independence, which is equivalent to this definition of independence. So here's a problem. You have a table. This is one you had before in a previous problem, and is a contingency table based on your age. Are you more likely, less likely, or neither more nor less likely to buy if it says made in American? And what we're supposed to do is figure out, is this event independent with this event? You know what to do. Let's see how you did. Well, those two numbers are different, so they are not independent. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.